so that as this wire goes into the magnetic field, that leading edge has, which is filled with electrons. They all experience a force. That force pushes them around. And because the forces on the top and bottom wire act in such a way as to not be able to move the charges because of the way the wire is oriented relative to the magnetic field, you can generate a current. And the generation of that current will occur until the entire loop is in the magnetic field. And then, of course, the forces on the leading edge and the trailing edge are in the same direction, so we get no current in the wire. Remember all that it was just the other day. And I think when we did that, you should recall that the EMF was the size of the magnetic field, the length of the leading edge wire, and how fast we pushed it into the area with the magnetic field. This was called motional EMF. And there's two things about this that I think are relatively easy to understand. The first is that the EMF that's produced is clearly proportional to the velocity. That occurs because of the simple concept of the force on a charge-carrying particle that's trapped in a magnetic field. That's where the V clearly comes from. The L, I hope you remember, the L comes from the fact that there is a competing force, the force from the electric field, and the EMF has to do with that electric field and the length of the wire. Again, should already be in your notes. We already talked about this, but this is where the L comes from, which is why the size of the loop didn't matter as much as just the size of that leading edge portion of the wire. The magnetic field, I think, is obvious where it comes from. It's still right there in our equation for B. We just studied this using net force. We said that when the net force is 0, we have pushed as much charge as we can to the top portion of this wire, and the electric field that's established balances the magnetic field, and the charges are kind of trapped up there. When we connected the rest of the wire, it was just to keep pushing them around, but the EMF produced is still based on B, L, and V. Faraday changes the script on this a little bit. Although motional EMF, I think, is easy to understand, Faraday postulated that the generation of the EMF wasn't just about the motion of the wire. What he said was, and this is where the note part, I think, begins, that any change to magnetic flux in a loop of wire will generate an EMF. Any change to magnetic flux in a loop of wire will generate an EMF. Any change to magnetic flux in a loop of wire will generate an EMF. Did I say it enough times? Now, like anything else in this class, no definition is complete unless we have some overly complicated looking equation to back it up. So let's get our equation to back it up, right? We'll start with the symbol for an EMF, script E. Now all we have to have is a change in magnetic flux. So change is always based on the derivative. So in this case, we're talking about the rate of change of something with respect to time. And then symbol for flux, put a little B subscript down here to remind us that we're talking about magnetic flux. Now that would be simple enough, except it's talking about a single loop, but as we're really aware, you can have a coil of wire, which would ramp up this EMF because you would have lots of loops experiencing this change at once. So we put an N out here to represent the number of possible loops that are being exposed to this changing flux. And then just to make it weird, negative sign as well. The negative sign, however, is a product of something called Lenz's law, which we'll talk about probably not today, but probably in a couple of days. Again, this part is the part that we really credit to Faraday. Now that looks pretty concise and pretty straightforward, and as you probably could gather from our conversation, it is exactly what I said. Any change in magnetic flux will generate an EMF. That's what's there. There's not a lot of nuance here, except it probably would make sense that we have some, some equation for how we calculate flux. But this is not like Gauss's law where we had to have a three-dimensional bounded surface. The flux in this case is any flux bounded by an area. I don't have to have a little circle here because we're not talking about a three-dimensional surface that requires bounding like we did for the electric flux in Gauss's law. This is just an integral because we're summing up how much magnetic field is passing through an area. And that's all this is. And put it in English in your notes. It's a sum. We're adding up how much magnetic field crosses an area. That's all we're doing. So it is a sum. Now the reason why we have an integral there, I hope that's obvious, but maybe it's not. The integral is there because what if the magnetic field isn't constant across your area? Well, then you would have to sum the pieces of it. Or what if your area is some kind of weird shape? Or what if your area is at a weird angle? If there's any kind of thing here, this is the dot product between the direction of the magnetic field and the direction of the area. So all of those things have to play a role in how we calculate this. But it's just a sum. And we have to remember that it could be a simple sum, like literal addition. So although we write the integral symbol here, even in this class, we're going to try and find ways to mediate that integration, to try and make it something that either is something we can work with or something we don't have to integrate at all. So let me show you an example of how we use Faraday's law. And I want to use the example that's right in front of us. For Faraday's law to truly work, or at least to be validated by experience, it would make sense if the experiment we talked about, the motional EMF, would have the same result whether we talked about it from the standpoint of Faraday's law or talked about it from the simple rules of forces on charged particles, meaning it should produce the EMF of BLV. Does that make sense? So let's back this up and see if we can set up Faraday's law in relationship to this exact example. So I'll put my other little X back in there that I erased for whatever reason. And let's define a few parameters first. Let's state that our loop is passing into the region of space that has a magnetic field with velocity v. Let's say that at this moment in time, I am freezing a particular moment in time. Now that's going to be something you're going to hear me state a lot in these problems because almost all of these are going to require movement of some sort, right? So either the magnetic field is moving or changing, or the loop is moving and changing relative to the magnetic field. So there's going to be a motion of some sort. Now, for that to be true, we need to take an instant, freeze it in time, so we can express what the flux is. Now, it might be moving, but we need to still freeze an instant. Does everyone understand? So your step one is to kind of define, and I hate doing steps, but in this class, but I think if I don't, we have trouble. So step one is to really define the geometry here. Simple stuff, define it, but you have to define it for a single instant in time. And you should probably choose variables that make sense for that instant. For example, I'm going to choose a variable here since I want to know how much magnetic field is in this region of space. I'm going to calculate flux. But flux only occurs when there's magnetic field passing through an area of the loop. This is the only region in which there's magnetic flux. My loop can be bigger, but this is the only region where I have flux. So because of that, I'm going to define this as having X amount of loop inside the magnetic field. Now, can we agree that X and V are related? Right? Do you understand X is going to be getting bigger for a while? And how fast it gets bigger depends on V. In fact, by definition, and I know you guys aren't all in mechanics, so let's remind ourselves, by definition, velocity is the rate of change of X if my loop is going in the X direction. And for all of you who had just AP1, delta X over delta T. It's the same thing. Now, I need to define something else. So I will define L because I'm going to want to calculate the area here. And I want to calculate how much of the area of our loop is exposed to the magnetic field. Now, if you wish, we could also assign a value of W to the size of the whole loop. I'm not sure what the usefulness of that is, but it might show up sometime. And of course, the magnetic field has magnetic field size B. So I've defined the geometry here. Your step one is to kind of define the geometry and freeze a moment in time. Your step two is always going to be come up with an expression for the flux. So always go to defining the flux next. And although it's an integral, we're almost always going to try and find ways to deal with the geometry of that integral. And some of it's going to be really easy. Like in this case, our magnetic field is constant. Right? It's the same value everywhere in that region of space. So for a sum, I think we know that the magnetic field is going to be the same value for every portion of our sum. The dot product is the alignment of the magnetic field with the direction of the area. Now, we've talked about that before, but you will still have to assess it. So in the case of this problem, I think it's pretty easy to say that the magnetic field and the direction of the area are aligned because the direction of the area is either out of the board or into the board. You follow? It's just a flat, square piece of wire, a square loop. So since the direction can either be perpendicular out or perpendicular in, it doesn't really matter which one of those we choose. Because this flux isn't bounded, and because our area is a plane, we can define what direction is the positive direction for area. Now, you guys a bounded area. So again, we can choose positive or choose negative because our area isn't bounded. So I'm going to choose that the area is into the board and that our magnetic field is into the board. That dispenses with the dot product by giving us a cosine of 0. All good? So all that leaves for me is to sum up the area that is being exposed to the magnetic field, which for this case, B times L times X. Right? The area exposed to the magnetic field is the length of the leading edge of the wire and how much of that wire is inside the magnetic field. Now I know X is changing, but we have frozen a particular instant. Does that make sense? Everybody okay with that? All right. So we now have defined our flux. We have an expression for the flux. So part 2 is get an expression for the flux. We have that. Now, part 3 is just to assemble Faraday's law using our new expression for the flux. So this is the shape of Faraday's law. So let's go ahead and assemble Faraday's law. The EMF will be equal to minus N d flux dt. N is the number of loops. I told you the negative sign is Lenz's law. Leave it in place for now. And I'll explain a little bit about what we have to do with Lenz's law, but not a lot yet. So now I'm going to replace this placeholder for flux with the expression we just generated. Now to complete Faraday's law, and it's refreshing, although we had to take an integral first, we have to take a derivative now. So every time you do Faraday's law, it's a 2-step process that involves taking an integral and taking a derivative. The integral is about area, but the derivative is about time. It's worth getting in your head because you guys are still fresh in calculus for most part and still sometimes get a little jumpy. So you might want to put next to part 2, this is about area, and part 3, this is about time. All right, so when I look at those 3 variables that I have to take the derivative of, the magnetic field isn't changing with respect to time. It just passes through the integral, or I'm sorry, passes through the derivative. So I'll pass the b outside the derivative. The length of the leading edge of the wire isn't changing with respect to time. So I can just pass that one right out of the derivative. And now all that's left is x. X is changing with respect to time, right? How fast I'm pushing that loop in is the rate of change of x. So putting in the 1 for n, we get v for dx dt. Now, this isn't a surprise. This should be exactly what we expect. The only difference is that our answer has a negative sign, and we didn't have a negative sign in our discussion from earlier. But do you see how Faraday's law works, at least in this particular instance? Now, let's discuss the negative sign, because the negative sign is what's known as Lenz's law. And there's a lot to talk about with Lenz's law, but the biggest and most important thing is that Lenz's law tells us the direction of the EMF, or more importantly, the direction of the current. That's what Lenz's law is about. But there's more to it than that, and I need you to understand a big part of it. Lenz's law is a consequence of conservation of energy. And ultimately, it's going to be about inertia in electromagnetic circuits. I'm going to say that again because if you understand this, it will make a huge difference. Remember how important inertia was in mechanics? Where if you had a good understanding of what inertia did, it would really help out with understanding how mechanical systems behaved. Lenz's law is like that. So Faraday's law is relatively cut and dry. If a magnetic flux changes, there's an EMF. Lenz's law tells you the direction of that change and will eventually tell us other things about circuits. So it's a consequence of conservation of energy. You can't get something for nothing. In fact, this speaks to David's question just yesterday about, well, aren't we creating energy from nothing? No, and this is the consequence. This is where it comes to be. So Lenz's law is a consequence of conservation of energy and will act like inertia. Now, and here's what I want you to think about. A couple of things. First, if I had just hit this loop of wire outside, like just gave it a velocity, and it was already moving, that loop of wire would have kinetic energy, right? Because it's got mass, because it's moving, there'd be some amount of kinetic energy. Now, when it passes into the region of space where there's a magnetic field, we know a current is going to be generated. And if there's a current generated, regardless of whatever the wire is, there's going to be some kind of power dissipated in that loop, which means energy is going to be expelled in that loop. That energy just can't come from somewhere, and disappear. We can't create energy without there being some other consequence in the universe. Meaning the only way we're able to push this wire into the magnetic field is if when we get to that point where the wire is entering the magnetic field, something happens that requires external work to be done. If that doesn't happen, then the amount of energy in that loop has got to decrease to match whatever energy is dissipated by the loop. Now, if you don't understand the consequence or what I'm talking about, then a current is developed in this loop, correct? We played with that idea just the other day. What is the direction of that current? Can you guys do a little math there? You're going to be doing this sucker, right? One of those. So clockwise. What I didn't bring up the other day is if there's a current this direction in the wire, what happens to a current carrying wire in a magnetic field? If you have a current carrying wire in a magnetic field, the current carrying wire must experience a force. So the magnetic field pushed on the charged particles, we know that, but this created a current now. a set of moving charged particles in the magnetic field. If I use my right-hand rule again, pointer finger in the direction of the current, middle finger in the direction of the magnetic field, there must be a force on the wire this direction due to the current we're creating because our loop passes into the field. If I want that loop to make it into the field without its velocity changing, I would have to apply an external force on the loop, or else this force would try and stop the loop from entering the field. You guys follow that a little bit? You want me to walk it through you again?
Can you say it again?
I can say it again, sure. So, getting back to the beginning. If this loop was just given a velocity, it's moving towards the magnetic field. There's a current created because a single charged particle in this wire right here, this positive charge, is moving to the right inside a magnetic field. Due to F equals QV cross B, there must be a force on that single charged particle that is upwards in the wire. I'm just talking about the force on this little guy right here. Is that okay? So just on this guy, and then every other particle that's in that wire also gets that same force, right? Now, yeah, there's also some in this guy, but that's going to be upwards, and there's nowhere for them to go. And there's also going to be on this wire, and that's going to be upwards, but there's nowhere for them to go. But these guys can go, right? So they all start moving upwards. And when they start moving upwards, yeah, it's counterclockwise, right? So suddenly we get a current that is counterclockwise in the wire. The current is this way. But I only care about the current that's in this part of the wire for right now. So I'm looking at the current that's in this part of the wire. Well, now there's a current in the wire. Well, because there's a current in the wire, there must be a force on the wire due to this current. That force has to be I-L cross B. I-L cross B. That puts a force on the wire from this current. And that force has to be this way. Now that's going to slow the loop down, which is what we would expect. We expect that if this thing has kinetic energy and you start generating a current, that current is going to that's going to make power be dissipated in this loop of wire. That energy has to come from somewhere. It comes from this kinetic energy that the loop had. If I want the loop to maintain the velocity and not slow down, somebody else has got to do external work on the loop to get it in there. Or else the loop's going to slow down. Now, look, this is how you stop a roller coaster car if you don't want to use physical brakes. Physical brakes wear out. One thing you can do is just put a bunch of loops of wire on the outside of the roller coaster car and have a magnetic field in the station where the cars are coming. It's a magnetic inducting braking system. All electric vehicles, all of them that recapture energy using inductive brakes use this, a form of this that recaptures the energy and brakes the car by generating a current. So instead of applying physical brakes, all you do is engage a magnetic field. And that magnetic field slows the car, generates a current. Now, I want to keep going with this because there's a consequence outside of this that has to do with Lenz's law. And that's where I'm really wanting to go. So clearly, and if you want to write a big banner point down, this will be important. Nature has a way of dealing with energy, and it feels like inertia is part of that way. In this particular case, there's a resistance, and I don't mean electrical resistance, there's a resistance to pushing this loop into the magnetic field. You want to generate energy, it's going to take work to do so. Our system resists change. Now, pay close attention to what I'm going to talk about here. I want to talk to you about what happens when this current is created, beyond the force that's created. When this current is created, everywhere in this loop, there is current. And like Anthony says, it's counterclockwise, right? Good?
Can you show that?
I've done it twice.
One more time.
That's exactly right. Pay attention, folks. This is the important thing I want to bring up here for Lenz's law. This current generates its own magnetic field. This is a current loop. And we know already that current loops create a magnetic field. Using the right-hand rule, there is a magnetic field produced all along this length of wire right here that is out of the board. And this is true everywhere in the loop. So there is a new magnetic field being created that is out of the board. Nature opposes the change. The current that's being created opposes the change in flux. So a magnetic field is being created to try and cancel the change in flux. I'll say it again. Nature opposes a change. Write it down. Get to the point where you're writing notes. Can I say the whole statement, please? Nature opposes a change. Therefore, a magnetic field will be generated in the loop that opposes the change in flux. You see, we're trying to push the loop into the magnetic field. We're trying to fill the space with a magnetic field that's into the board. So the loop on its own generates a magnetic field out of the board to oppose that change. If you were there, if you were holding onto this loop, you would feel resistance. It's like trying to push two magnets together that are opposing each other. That's the force you would feel because it's trying to oppose this change. And it does so by creating this magnetic field that opposes the change in flux. Okay. This example is designed to be super easy for you to understand the direction of everything. I thought it would be. And we've gone through it many times now, but my whole hope was that I was able to use a simple rule to begin with to help convince you of the direction of the current, and then another simple rule to help us deal with this new magnetic field that might be created and the force on the wire from it. That's what my goal was, because Faraday's law actually states that any change in magnetic flux generates a flux. Any change in magnetic flux generates an EMF. So consider something a little more esoteric. What if I have a square loop of wire in a magnetic field? I know I only have like 2 minutes. But instead of moving this loop into or out of the magnetic field, I just turn the field off so that the magnetic field dies out. Would that constitute a situation in which there's a change in magnetic flux? So let's say that's what I'm doing. I have a magnetic field into the board, and I'm going to turn it off so that it decays over the span of, say, a minute or two. So a slow decay of the magnetic field. That would have to generate a current in that loop. Lenz's law is there to help us figure out the direction of the generated current because I don't have anything motional happening. I'm not pushing something in. I can't use QVB or ILB. It just says just because the magnetic field disappears, a current is being generated. Now, if the magnetic field is dying out, the loop's going to generate a current to try and keep it there. So what direction must the magnetic field that's being generated be? Into the board or out of the board? into the board. What direction would the current then be in order to produce a magnetic field into the board? Clockwise. That's right. It would have to be a clockwise current. That's how Lenz's law is there to help you figure out the direction of a current produced under any circumstances.